So let me sort of start with p-adic groups. So for me, F is always going to be a finite extension of QP. And G is going to be the group of F points of a connected reductive group over F. So, I mean, I'm sure everybody here knows these things very well, but let me sort of start out very basic. You could take your G to be something like SL2QP, GL2QP, a symplectic group over QP, or, you know, if you want to be more exotic, you can take an exceptional group like E8 over QP. So any group of that looks like this, but for the most part, all of my examples are going to come from SL2QP. So if you just want to think about that, that's fine. So the main theme is going to be the representation theory of p-adic reductive groups, and I'll sort of define that a little bit more precisely in a little bit. But I want to start with some examples so you have some things to sort of hold in your head if you've never seen these things before. So let me give two sort of very basic examples. So the first starts off as follows. So let's let P1 of QP denote the projective line over QP, which we're just going to endow with its p-adic topology. No sort of scheme theory here or anything like that. And again, I'm going to focus on SL2QP for all of my examples. So the group SL2QP acts on P1 by Mobius transformations. So if I have a matrix A, B, C, D, which lies in SL2QP, it acts on the homogeneous coordinate X, Y in the following way. So just doing the standard thing. Okay. So this is my space. And anytime I have a group acting on a space, I can linearize to get a representation. So the next thing we're going to do is we take an arbitrary field C and consider the following C vector space. So the vector space is all C infinity functions from P1 of QP to C, to the field C. And what do I mean by C infinity? Well, I haven't told you anything about this coefficient field C. So the only reasonable thing you could impose to get any notion of continuity is for your function to be locally constant. So that's what I'm going to do. This makes sense. And since I've sort of essentially dualized the picture, I get an action of SL2QP on this vector space of functions just by acting by G inverse on the argument. So the element G from SL2QP acts on a function by multiplying or by acting on the argument by G inverse. So this is sort of a standard thing. And so this vector space equipped with this action gives me an example of a smooth infinite dimensional representation of SL2QP. And just to remind you, again, I know everybody's sort of seen this from, for example, Charlotte's talk this morning. But just as a reminder, smooth means that every vector has an open stabilizer. So for every function from P1 to C, there's going to exist a compact open subgroup of SL2QP which fixes F. And this follows from the local constancy of F. And maybe just to make sure we're trying to understand these things as best as possible, the other thing I'll mention is that this representation is not irreducible. So for example, the subspace of constant functions is always a vector subspace, and it's stable by the action of SL2QP. Okay, so that's sort of the first example that you can keep in your mind, fairly basic. And so let me upgrade this a little bit. So now we're going to define B to denote the upper triangular Borel subgroup of SL2QP. And I'm going to choose a smooth character chi from B into my sort of arbitrary coefficient field C. So again, this character chi is smooth, which in this context, again, means it's locally constant. So we have this, this character, and out of this character on B, we can form the following vector space. So again, it's going to be some vector space of functions, this time on the group G going to C, where again, I impose this local constancy condition But moreover, I'm going to impose this sort of functional equation. So if I take the argument and multiply it on the left by something in this Borel subgroup B, then I can pull that out at the cost of multiplying by this character chi. So you can think of this as being some, I say this is an upgrade because you can think of this ind BG as being some sort of space of global sections of some local system on P1, if you like. But if that doesn't make sense, just think about it with this definition. So I'm going to sort of just move this up. And what we do is we equip this space with a left G action by the following rule. So in this case, I'm sort of acting on the right in the argument here. And I won't go through it, but it gives me a well-defined action of G, which is SL2QP on this space. And once again, this procedure gives me a smooth infinite dimensional representation of SL2QP, which is generically irreducible. So if I sort of pick my character chi at random, whatever random means, there's a good chance you're going to get a irreducible representation. And furthermore, if I take the trivial character, then this just reduces to the previous example. Okay, so these are some examples to sort of keep in the back of your mind. And so now why would anyone care about representations of these big p-adic groups? Well, one of the main motivations comes from studying, or comes from the local Langlands program, which sort of aims to connect these representations to representations of local Galois groups. So this is sort of a very rich area of study. And maybe let me not say too much more about this, but this is somehow why people want to have a good understanding of representations of p-adic groups. They want to relate it to arithmetic information on the Galois side of some sort of Langlands correspondence. And for most of what I'm going to be interested in, I'm going to take this field C to have characteristic P, which oftentimes people are quite afraid of, and I'll sort of indicate why going forward. But taking or understanding such a correspondence with mod P coefficients has applications to the p-adic Langlands program, which is a relatively recent and important variant of the classical Langlands program. And so my goal is not to really talk very much about sort of the Langlands bridge, but let me just give an indication of how important this p-adic version is. So one of the consequences of this p-adic Langlands program, just for the group GL2 over Q, is many cases of the Fontaine-Mazur conjecture, which states that a continuous irreducible Galois representation from the absolute Galois group of Q going into GL2 QP bar, which satisfies a short list of natural properties, natural here sort of in the colloquial sense, actually arises from a cuspidal eigenform. So let me not actually list what these properties are, but it's something you would naturally impose on such a thing. So if such a Galois representation looks like it comes from a modular form, then it actually does. So this is a very striking result, and it was proved using techniques using results from the p-adic Langlands program. Right, so the attributions here, it builds on work of many other people, but it was sort of taken care of by Emerton, Kissen, and Pan. Okay, but now let me sort of move on and sort of focus only on the automorphic side of things. So on the representation theory of p-adic groups side of things. And what I want to focus on is this notion of duality. So a standard tool when dealing with representations of a general p-adic reductive group G is that of taking the dual representation. And so, for example, this is extremely useful because if I say take coefficients in the complex numbers, dual representations appear in functional equations of automorphic L functions. So it stands to reason that I would want to know as much as possible about this procedure of dualizing. So let me give the precise definition because it's going to sort of come into play later. So if I'm given a C vector space, and again, C here is going to be an arbitrary field until I say otherwise, with a smooth action of G, then I'm going to define v check to be the following thing. So it's some union over v star upper k, where this v star is just the linear dual of the vector space v, which is equipped with a not necessarily smooth action of g. So if v is infinite dimensional, for example, the action on v star is not going to be smooth anymore. And this upper k just denotes the subspace of k invariant vectors, where k is my compact open subgroup. So essentially this procedure of taking k invariants and looking at all, taking the union is some process of smoothification. So this v check is going to give me a smooth representation of G once again. Yeah. So this is the definition of dual that is usually useful. Right. And so when I take my coefficient field to be the complex numbers, or even more simply just characteristic different from P, this functor of taking V and passing to its smooth dual has many nice properties. So for example, it is exact, and we have some familiar double duality. Sort of this double dual is canonically isomorphic to V for admissible representations V. So, and I'll remind you, admissible here just means that the space of invariant vectors is finite dimensional for all compact open subgroups. This is nice and has sort of properties that we would want. Unfortunately, on the other hand, when the characteristic of C is equal to P, which again is going to be the case I care about, this functor of taking the smooth dual is no longer exact. And maybe I'll just give a rough reason why that is. This group G, so again, it's the group of F points of a connected reductive group. Such a group is locally pro-P. So if I sort of take a neighborhood basis of the identity, eventually those neighborhoods are going to be pro-P subgroups. And taking invariance by pro-P subgroups in characteristic P is not an exact operation. And perhaps, maybe more strikingly, if you've never thought about these things, is the following result. So let's suppose that our coefficient field is characteristic P, and that V is a smooth, irreducible, admissible representation, which is infinite dimensional. So then this smooth dual is actually zero, reduces to the zero representation, which is quite different from the case of complex coefficients. And so this lemma is sort of almost folklore. I've seen it attributed to many different people, but one place you can find it in print is in an article of Kohlhaase. Okay, so this is a bit striking. And what I'd like to do actually is give a sketch of the proof, just to sort of indicate where this characteristic P assumption is coming in. So, you know, you can, if you don't care about the proof, you can just sort of turn off your brain for a sec. So the way this goes is if we let K denote a compact open subgroup, then this admissibility condition on V implies that the linear dual is going to be a finitely generated module over the Iwahori algebra. So this Iwahori algebra is just an inverse limit of group algebras of the finite quotients of K. So it's some sort of, you know, compact or rather pseudo-compact ring. And the important feature of characteristic P is the following result. It's that this Iwahori algebra, when the coefficient field has characteristic P, is actually Noetherian. So this is a feature which no longer holds if the characteristic is different from P. So I have this Noetherian ring, which means that this submodule, this smooth dual, is also going to be finitely generated. Okay, so this is a characterization of being a Noetherian ring. Any submodule of a finitely generated module is itself finitely generated. And so if we pick a set of generators and let Ki denote their stabilizers, by smoothness, these are going to be open subgroups. And we can write this smooth dual in the following way. So again, you don't have to worry so much about this, but the conclusion is that this implies that the smooth dual is actually is finite dimensional. And in particular, cannot be equal to just the regular linear dual. Okay. So that's sort of one side of the story. So we've used sort of smoothness and admissibility and infinite dimensionality. Okay. So again, the linear dual is something familiar, and in particular, this is infinite dimensional. What we haven't yet used is this irreducibility assumption. And the way this comes into play is that this linear duality functor is essentially a version of Pontryagin duality and gives an anti-equivalence of categories between smooth representations and pseudo-compact modules over this ring, which I have not defined for you, but this is only a sketch, so I'm gonna sort of let that be my excuse. In particular, since V is irreducible on the smooth side, its dual is going to be simple on the pseudo-compact side. And so I have a simple module and a proper submodule, which implies that it actually has to be 0. So the key feature, which is really either screwing things up or making things a little bit nicer, depending on how you look at it, is that this, this Iwasawa algebra is a Noetherian ring. And this is sort of very specific to characteristic P. Okay, so are there any questions on this result before I move on? So again, maybe this is sort of not surprising, but I remember being quite surprised when I first learned about this. In any event, what we want to do is we somehow want to remedy this deficiency, or remedy these deficiencies with these duality functors when the characteristic is equal to P. So in order to do this, Kohlhaase defined a sequence of higher smooth duals given by the following formula. So, so I take my representation V, and again, I take its linear dual. And then instead of looking at invariant vectors by K, I look at X groups. So Xj of the trivial module over this Iwasawa algebra. And then sort of the appropriate analog of union is taking a direct limit. And this thing ends up being equipped with a smooth G action. Okay? So I've taken my representation V and produced another smooth representation out of it. And so let's just note that if I take J equals 0, then I get a Hom here. And again, this sort of reduces, this inner thing reduces to the space of K invariant vectors. So sort of taken as a whole, this sequence of functors is much better behaved and actually gives a contravariant delta functor from the category of smooth representations to itself. And I mean, you can do a little bit better. You can define some sort of total functor on the derived category, if you like. And maybe something I'm going to insist upon is that, you know, you can actually do calculations with these things. So if I go back to, you know, my favorite example of SL2QP and let V denote this representation, this induced representation as before, then these smooth duals are non-zero if and only if J equals 1, in which case the first smooth dual ends up being another induced representation, and it has this specific shape. Okay. So I just take the inverse of the character chi, and then I have to sort of adjust by sort of this positive root alpha. Okay. So that's sort of the first part of what I wanted to say. Are there any questions up until here? Okay, so I'll keep going. So we essentially have this nice duality theory on smooth representations. Now I want to say a few words about Hecke algebras and why we care about these Hecke algebras. So from now on, I'm going to assume that my coefficients are actually FP bar, although really any field with characteristic P will do. And so the goal is to develop a version of Poincaré duality for this sequence of functors, a sequence of higher smooth tools. And the tool I'm going to use for this is these Iwahori-Hecke algebras. So let me describe what those are for you. So I'm going to let I denote an Iwahori subgroup of G, and I1 its pro-P-Silo subgroup. And again, if you've never seen these things before, you can keep this example in mind. For SL2QP, the Iwahori is simply just all matrices which are upper triangular modulo P. And this pro-P Iwahori, which is maybe a little less common, is all matrices which are upper triangular and unipotent modulo P. So out of this, I'm going to define this pro-P Iwahori-Hecke algebra with the following definition. So it's just the set of all compactly supported functions from G to FP bar that are invariant by this pro-P Iwahori subgroup on both sides. So again, it's just compactly supported I1 by invariant functions. And there is a convolution operation on functions, which actually gives this the structure of a non-commutative algebra. So this is different from, say, the spherical Hecke algebra that you would see in the theory of modular forms. This is a non-commutative analog. But nevertheless, it still has a simple combinatorial description that makes it useful for doing calculations. So again, let's go back to SL2QP. And actually, instead of giving you the structure of H, I'll give the structure of H prime, which is the Iwahori-Hecke algebra of G with respect to I. So it has the same definition, except here, instead of being bi invariant by I1, I'm just sort of making the group a little bit bigger and letting it be invariant by the Iwahori subgroup. This guy has sort of a nicer presentation and is very closely related to the actual Hecke algebra that I care about. So this will be a certain quotient of this algebra. But in this case, we have that this H prime is generated by two functions, T0 and T1, where Ti denotes the characteristic function of this specific double coset. Okay. So when I equals 0, then this is just a reflection in the Weil group. And when I equals 1, it's a reflection in the Weil group sort of adjusted by P. And there's only two relations in this Hecke algebra, which are the so-called quadratic relations. And they look as follows. So if I take one of these operators and square it, I get this relation, which works over Z. But in our situation, since we're in characteristic P, this actually simplifies just to minus Ti. So in characteristic P, these Iwahori-Hecke algebras are, the presentation is much simpler. And if I were to take a group that's bigger than SL2, if I were to take SLN, I would still have these quadratic relations, but then I would have also what are called braid relations, which come from the presentation of, say, an affine Weil group. Okay. So this is sort of the Hecke algebra that I want to be dealing with. And again, for the actual Hecke algebra H, there's a completely analogous generators and relations presentation. And there's an analog of the quadratic relations, but they're just a little bit more tricky to write down. So I want to sort of not do that. But okay, so I've defined this Hecke algebra H. So now I should tell you why it's useful. So the idea is that this Hecke algebra can be used to understand smooth representations of G using the following procedure. If I start with a smooth G representation over FP, then the space of invariance actually admits a right action of this Hecke algebra. If I1 happened to be normal, then this space would actually get an action of the whole group G. But in general, I1 is not normal. And so what I'm left with is an action of this Hecke algebra. And so what we get is a functor from the category of smooth representations to the category of modules over this H. And maybe I'll just say that for very special choices of G, this functor actually induces an equivalence of categories between a certain full subcategory of this category of smooth representations and the category of modules over H. Although this equivalence is sort of known to fail in other situations, so this is not really what we want to rely on. Again, going back to the favorite example, if I take G to be SL2QP and V to be the trivial representation, then the Hecke action on the space of invariance, which as a vector space just ends up being FP bar itself, actually factors through this H prime, and these two operators T0 and T1 act by 0. So this is something that's, again, very computable. So how can we push this further? So since the characteristic of FP bar is equal to P, and this group I1 is pro P, the functor of invariance is not going to be exact in general. So it makes sense to try to take derived functors in order to sort of tease more information out of this. And so assuming I1 is torsion free, Schneider showed that the derived version of this situation, which sort of looks as follows, going from the derived category of smooth representations, the derived categories of certain modules over a certain algebra H bullet, which I'll describe in a second, actually yields an equivalence of triangulated categories. So as long as this I1 is torsion free, then we can understand the entire derived category of smooth representations by looking at some sort of modules over a Hecke algebra. And this H bullet is, well, what is this? This is a certain differential graded algebra closely associated with H. So this H bullet has a differential and its zeroth cohomology is isomorphic to this algebra H that I started with. Okay, but the issue with this equivalence is, at least for me, is it's hard to get tangible information out of this. So what we can do is we can sort of come back down to earth and pass to cohomology to obtain derived functors. And so if we sort of do this, we'll get functors going from the smooth representations of G back to modules over this sort of nicely presented Hecke algebra that we started with, just given by looking at I1 cohomology. And just like with the space of invariance, this cohomology space admits a right action of the algebra H. And the point is that these cohomology spaces are more down to earth. You can even use like cocycles to compute these, and they're a little bit more easy to work with than this sort of big derived complex here. And just to give you an idea of how these are more down to earth, again, if we go back to this favorite example of SL2QP, and if we assume P is greater than or equal to 5, this guarantees that the pro P Iwahori is torsion free. If we go back to the trivial representation, then we have H module isomorphisms. So H1 ends up being isomorphic to H2, and this ends up being isomorphic to the I1 invariance of this induced representation. And H3 actually ends up being isomorphic to this representation that I described before for just the invariance of the trivial representation. And everything else is 0. So these things have a better chance of being computed than this total derived functor from the previous slide. Okay, so this is sort of the setting that I'm working in and that I'm trying to understand. And so now finally I can state the results that I sort of mentioned at the beginning. So I can state the main result, which relates Kohlhaase's smooth duals to this pro P Iwahori cohomology. And so this theorem was also proven by Schneider and Sorensen using sort of very different techniques. So I should sort of mention that. And the assumptions are as follows. So assuming that I1 is torsion free and V is any smooth G representation over FP bar, then we have a spectral sequence of H modules, which looks as follows. So it starts on the E2 page And on the E2 page, so I'm looking at Kohlhaase's duality functors, and then I plug, so again, these give me smooth representations. I plug them in to this I1 cohomology, and I look at the ith degree. And so this will converge to the following thing. So it's another cohomology group where here I'm taking the dimension of G as a QP, as a manifold over QP, minus I minus J. And I'm taking the coefficients in a different representation. So I should describe this for you. So what does the star denote? Oops. This denotes the Hecke module whose underlying vector space is the linear dual of whatever I start with. And this Xi or is a certain orientation character, which I'll describe in just a second. So this is what I'm calling this Poincaré duality spectral sequence. And what this really is, or how it can be thought of, this can be thought of as essentially an H equivariant version of something which shows up in Galois cohomology. This is called a Tate spectral sequence. This is, you can read about this in one of the appendices in Sarah's Galois cohomology. Right. So this is the sort of the main result, and I want to maybe talk about a few more pertaining results, but are there any questions on this theorem just before I go on? Okay. And so just maybe a few words about the proof. So the proof uses essentially results of Lazard and results about the cohomology of p-adic analytic groups, compact p-adic analytic groups with sort of pro-finite coefficients. So there's sort of a lot of things that have to be taken care of and worked with. Right. So what happens, or what sorts of results can we deduce out of this thing? So one thing that one can notice is that these functors, Sj, these higher duality functors, are quite computable for various classes of representations. And this can be used to deduce information about these Hecke modules. Okay? So perhaps I didn't indicate this very clearly earlier, but what I'm really after is trying to understand Schneider's derived equivalence. Okay? This involves the entire sort of derived category of smooth representations. And this is what we want to understand. And this would be like, taking the cohomology would be, the first thing one would consider. And so let me give sort of an instance of when this happens, when these things are easy to compute. So if I take the trivial representation of any reductive group G, then this first smooth dual ends up being just the trivial representation again. And anything above ends up being 0. So what this implies is that the spectral sequence from the previous slide sort of immediately degenerates and takes on a more familiar shape, which I'll sort of make clear what I mean by that. So supposing, again, I1 is torsion-free, as always, and V is the trivial representation of, again, G can be anything. We then have an isomorphism of Hecke modules, which looks as follows. So on the one side, I have HI of this pro-P Iwahori with trivial coefficients. And on the other side, I have sort of complementary degree with a dual and with coefficients in this orientation character. So this is perhaps a little bit more analogous to sort of Poincaré duality for that you would see in topology, where if I'm considering non-orientable manifolds, I always have to twist by this orientation bundle. Okay. So again, in certain situations, these duals are quite computable. And for example, knowing low degree information about these cohomology groups or these Hecke modules gives you information in higher degree. Maybe as another instance of the usefulness of this spectral sequence, for the groups SL2QP or GL2QP, one can actually compute all of these cohomology spaces as Hecke modules where the coefficients live in an irreducible G representation. So if the group is relatively small, then we have sort of complete understanding of what these cohomology spaces are. Okay, I have 3 minutes left, which is great because I think this is my next to last slide. So the only part I haven't really talked about is this orientation character C. So I'm gonna give the definition and then ask that you promptly forget it. So the definition is defined as follows. So given an element G in G, we define this value in FP bar to be the scalar, which is given by the following sequence of isomorphisms. So if I look at what happens on this right-hand side, I'm looking at this top cohomology of a certain profinite group. So it's I1 intersect with one of its conjugates. And again, assuming I1 is torsion-free, its cohomology is bounded. This is its top cohomology. And sort of results of Lazard imply that this cohomology space is one-dimensional. There's a canonical trace map. So what I do is I start from FP, I sort of take the inverse of the trace map to get to this group, and then I conjugate by G to get to another cohomology group, and then I take the trace map back down. So it turns out that this gives a character, first of all, so it's a homomorphism, which is not clear immediately from the definition. And again, if none of this made sense, well, that's fine, because it turns out this character has a much simpler description. So again, this was a result sort of first proved by Schneider and Sorensen, and was sort of another proof was found by myself and David Schween, who is a PhD student of Tasho Kaleta. And it turns out that this orientation character is always trivial, so regardless of what the group is. Okay, and so, well, on my last slide, I sort of have a sketch of how this goes. It's actually a very short proof, but maybe in the interest of time, I'll sort of go through this very quickly and just stop right here.
Thank you. Right. Any questions?
Can you apply this spectral sequence to, say, compactly induced representations of, say, the trivial representation of the pro-P Iwahori?
Oh, that's a great question. So, I mean, so you can definitely plug that in as your V. This spectral sequence works for any smooth representation. But I think you would have to have some information about what these what these are. And I think Klaus has thought about this a little bit. That maybe they vanish above the dimension of G mod B, if I remember correctly. But yeah, you could certainly do it. And I think I thought about this at some point, but it was hard for me to pull out any sort of new information. But
what do you take into BV?
The compact induction from pro-P Iwahori to G of the trivial representation.
Right. Yeah, in that case, they vanish beyond the dimension of G mod B. Yeah.
So perhaps there you could get some extra degeneracy of this spectral sequence. But yeah, this is definitely something to consider, sort of in Schneider's context. This sort of universal module is something that you want to understand the cohomology of as much as possible.
Yeah, there's nothing like Shapiro's lemma that simplifies it to give you information about to calculate in terms of I1 intersect B, for example.
There very well might be. I haven't thought about it recently, but yeah, that's definitely a great direction to go.
So is it known when I1 is torsion free? So like a precise bound on P? If it's SL2, you need P bigger than 5, or P bigger than 3.
Right.
So
So
take a general reductive group, how large do you have to take P to?
So if the group is simply connected, I believe, then there's a bound in one of Totaro's papers. That's I think it's sharp even.
Something like the Coxeter number or something like that.
Yeah, exactly. And it involves the ramification of the p-adic field over QP as well.
All right. Any other questions, comments?
When working with the Hecke algebras and presentations, it doesn't simplify things if it's split the reductive group, or works.
I mean, the presentation is it's slightly simpler. If you say work over Z, you don't have to worry about the parameters having different values. So for example, these Hecke algebras can be defined over Z. And so if you take a non-split group, let me see if I can go back to the presentation. So for a non-split group, you could have one generator which has a P and another generator which has a P cubed. That's what happens for like a unramified unitary group. But if you're working mod P, then I mean these sort of go away anyway. But the presentations for this have been given by Vigneros, for example, for a general reductive group. But I mean it's somehow no simpler. Somehow you just the generators are given by simple affine reflections in your affine Weyl group, and then you have some elements coming from the normalizer of the Iwahori.
All right, if there are no more questions, let's thank Karol again and take a 5-minute break.